Okay, do you all hear me? Do you hear me well? Also in the back? Yes, okay. So thank you so much, Nika, again, for having me here. Thank you, Harrison. Thank you, Bill, for the absolute impeccable organizing around the studio. Thank you to the studio and all the people behind. And thank you very much to the participants for bearing with me for the past 2 days and for finishing their instruments and making screaming minerals. I'm very excited to see how it will work out. So when I started this workshop, we were firstly just building instruments and trying to kind of figure out what a semiconductor is. So my practice is mostly I build instruments, I build in different synthesizers and installations and performances. But recently, in the last 2 years, I was really wondering like how electronics work to their core. So then I started this little research project in which I wanted to build my own transistor. And this workshop is kind of the result of this research, of which became a collective research. So I started to teach people how to build their own transistors. And then I thought, well, you know, when we do these performances, they're very noisy, they're very unpredictable, sometimes a little bit annoying. And I wanted to also show people what is actually behind these performances and what these instruments are. So therefore, I include a little talk before this. So at the end of my talk, we're gonna do the performance, and you are invited to come closer. Please do not walk through, and most importantly, please do not talk to the performers while they are trying to play their instrument. Yeah. Okay, cool. So I will start with this image. Does anybody know what this image shows by any chance? No. So that's what I also figured out. And then I started to zoom out, and I would see this. And then I would zoom out, and I would see this piece of equipment, and I would zoom out even more, and I would see my own device. So this is where my research started. I thought we have all these wonderful machines, these intelligent computers that are in our pockets. We use them daily. We almost have a relationship with them, yeah, like a passionate relationship. And we actually don't know how they look inside, which I think is a little bit odd. Yeah, so they look like this inside. This is a picture of a transistor seen with an electron microscope. So a transistor these days is very, very, very small, and there's like billions of them in a device. So I wanted to see what this is made of, basically. And then I discovered that one of these phones is made of 75 rare earth minerals. So 5 of them which are very scarce, such as cobalt, silver, copper, molybdenum, lead, chromium, indium, antimony, 6 which are abundant, such as silicon, iron, carbon, nickel, calcium, aluminium, 16 rare earth minerals, such as neodymium, dysprosium, niobium, germanium, europium, praseodymium, gadolinium, terbium, as I started to look at these 75 minerals, at the beginning I focused on one, which is galena. So galena is a very common ore. You might have heard of it in the form of lead, a quite heavy material. And the story of lead goes back all the way at the beginning of humanity. So one of the first empires that were using lead were actually the Persians. They made coins out of it. But then there is a very interesting case in the Roman Empire. So this, what you see here, is a map of the aqueducts that the Roman empires have built from lead. So as you might know, they were a very powerful empire. They started to extend, and most of that was due to the technologies that they were using. And one of these technologies was making running water into their houses. And how were they doing this? Well, they were using these pipes of lead. Why? Because lead doesn't corrode when it goes close to humidity. So this is a really great thing to do, but the only problem is that lead is also highly toxic. So when you drink from lead cups, or if you put, how they were also doing, they were sweetening their wines with lead powder because lead is sweet. Yeah. What happens is that because this is a neurotoxin, you can get impotent. And it is said that the Roman Empire might have fallen because of their use of lead pipes. So much later on, we have this scroll. This is Cleopatra the Alchemist, not to be confused with the other Cleopatra. And she's one of the first people that are able to achieve transmutation. What is transmutation? Well, in medieval times, most alchemists, so most chemists or scientists, were really preoccupied with how to transform a less noble metal, such as lead or mercury, into a more noble metal, such as gold or silver. So in this scroll that we have here, which is the historical scroll, she's giving us the recipe of how to transform lead into silver. This is this part here, if you see it. Also in the same scroll, we have this symbol, which might be a little bit familiar to some of you. It is an Ouroboros. It is a snake biting its own tail. It became also, I think, the sign of a publishing house. So this sign, first appearing here, it kind of alludes to the idea of feedback. So something that is perpetually happening. The same feedback that we will find later in our oscillators. So she says this: one is serpent, which has its poison according to composition, and one is all, and though it is all, and by it is all, and if you have not all is nothing. Another alchemist that also achieves transmutation is Maria de Profetissima. So she's also very much known for this machine. This is a bain-marie. You probably might have used it when you melted chocolate in your kitchen. So it's a double boiler, basically. So she's the creator of the bain-marie. And she comes with another interesting idea, and that is that a noble metal is formed when two types of gendered metal are combined. So she kind of genders metals, and she talks about hermaphroditism as being the supreme state of metal transmutation. Then later on we have this woodcut, and this is showing a mountain with veins. So where do all these minerals come from? Well, they come from earth. And how are they extracted? At the beginning, people found these veins on the mountains. Of course, all of these veins are gone because we took them out, most of them. So you would walk around and you would find a beautiful mountain and you would see these silver veins on it. And in order to take them out, at the beginning it was very easy. You would just use your tools and move them out. But as time went by, and this is the case of Cerro Rico, so the Spanish crossed the ocean. They stopped in Bolivia, or what is now Bolivia, and they found this one mountain which is full of veins. It's exquisite. It's shining of veins. So they're like, okay, let's start exploiting it. So they take the indigenous population and they remove the veins. After this is done, which takes around 50 years, they start to dig inside the mountain. And they dig and they dig. And as these workers start to remove the ores from the mine, of course they inhale the byproduct of silver, which is lead. So they get sick with silicosis. This is called the mountain that eats man, because more than 8 million people have died extracting silver ores. It is also said that between the 15th and the 18th century, 80% of the wealth in the world, and mostly in Europe, was coming from this one particular mountain. So here we can also see how this looked like from the perspective of an ice cube. So, you know, when you go to the Arctic or like in the North or South Pole, you can find very deep crevasses, and you can extract pieces of ice, and in these pieces of ice you can see the imprint of pollution that happened throughout the history. So this is a slice of ice where we can see the density of lead powder by just measuring and looking at it. And we can see this is the years where the Cerro Rico was mostly exploited. So you can see how this also looked like in air. Because of course, when you extract something and you pulverize it, this produces a lot of dust, and this dust is deposited all across the globe. So of course, if we were to put this graph and bring it until today, we will have a huge peak at some point, yeah, as our industrial revolution has moved forward. So more or less at the same time, Martine de Berthoreau, mineralogist, the first female mineralogist that we know of, writes this testament to the Pope. She's saying, well, you know, I have dedicated my life to the mines. So she's going and mining and also like investigating the mines that she can find in France. And she makes a book about all these mines, and she writes to the king saying, well, I think we have a lot of resources here in France, and we should start mining here. Of course, it is a year where doing this, you're most likely to be considered a witch. So in the same year, she runs to Hungary, but it's already too late because she will be killed as a witch. And then, as history goes by, people start to dig deeper and deeper in the earth. And later on, we have this researcher, and you might already know her. This is Marie Curie. She makes an interesting discovery. She finds out that as a piece of mineral, such as uranium, so she discovers radioactivity. Radioactivity is basically having a mineral emit a lot of energy. So she discovers that uranium, as it decays, it passes from stage to stage. So for instance, as it's in its teenagehood, it might be radium, then it will be radon, then bismuth. And when it reaches at the end, it becomes lead. So lead, in essence, is the same thing with uranium. It is just a stable form of uranium. Of course, it is not radioactive. Lead is not radioactive, but it still portrays some special properties. So here we go back to the galena crystal, the one crystal that is in all of our telephones, yeah, and all of our devices, and the one crystal that has powered our information technologies right from the beginning. So it seems that there's some more other crystals that do different properties, and here is a list of them. And if we are to look at galena, we will definitely have to look at radioanatomy. So galena is one of the first minerals that is used to transmit and receive a signal. And one of the first persons that does this is Jagandrish Chandra. So Jagandrish Chandra moves from India to United Kingdom, UK, that's better, to UK, where he's conducting his research on radiotelegraphy. And he's one of the first that is able to transmit a short wave from one side to the other without the use of wires. Of course, this is way before Marconi and all these people. And of course, Jagadish Chandra is more interested in the knowledge side of things, so he doesn't patent his discovery. Therefore, he's not recognized as the inventor of radio. So let's look at his machine.
If light waves can travel without the help of wires, why not electric waves? For their properties are the same. He proved upon his argument in 1895. He used an electric wave generator to fire a gun placed 75 feet away, even though the two were not connected by any wire.
So what did he actually do? Well, and to explain how this radio transmission worked, we can look at two tuning forks. So you might know a tuning fork, if you strike it and it goes like poo, you can use it for different things. But if you had two, if it happened that you had the same tuning fork by the same manufacturer, the same frequency, so they're the same size, if you striked one and you would hold the other one without striking the second one, an interesting thing would occur. The second tuning fork would start to vibrate. It would start to sound, although you have not touched it. And why is that? Well, that's because they're both at the same resonant frequency. So it's a little bit like speaking, yeah? If I were to speak in my own language, you will not understand me today. So we have to speak in the same language to transmit a signal. It's the same thing with this tuning fork. They are at the same resonant frequency. So when one starts to vibrate, those waves move through the air and articulate on the second one. So who is receiving all of this vibration? Who is receiving the telecommunication? Well, here is where our galena crystal comes back. This is a galena crystal from a crystal radio. This whole construction is called a cat whisker, and it is more or less the construction that inspired our devices. So you will find the same kind of needles touching different crystals all around. So this galena behaves a bit like a door, like all the doors in this university, as I noticed. You can go in one way, but you cannot come back. So you can exit, but you cannot enter. So this is how this galena is behaving. And when it's doing this, it demodulates the sound. So as the waveform come to the crystal, they're all kind of encoded in a carrier. And in order to hear it, we have to put it through this demodulation crystal. The crystal looks a little bit like this in modern format, and it sounds a little bit like that. I actually get a very bizarre transmission and oscillation here, which I cannot tell why it is. Very interesting. So here I have connected two of these crystals. No idea why this is happening. So there's a field around this table, not from my devices, but maybe from somewhere that is underneath. So we have this crystal that is able to transform complex signals into audio signals. And then we have two more parts. We have a coil and a capacitor, all connected. And this makes for a very simple device. You can build a radio from very few parts. This is an actual crystal radio. So because it's so easy to build, people started to build them from all various kinds of things. So here we have a ring crystal radio, an umbrella crystal radio. We have the famous foxhole radio, which was used during the Second World War, in which a rusty razor blade behaves like the galena, demodulating signals. And then in Netherlands, during the Nazi occupation, when the fascists took all the radios from the people so that the people cannot get any information, what did the people do? Well, they built their own radios and they hid them in everyday objects. So this is iron for clothes. We have a book radio. We have a medkit radio, kettles, thermos flasks, heaters, even a record player that could be converted into a radio, so you never see. So radios become a big culture, a big part of our culture, especially crystal radios. Here we have a lot of movements of radio amateurs that start to construct radios out of absolutely anything because they are so easy to build and they're so easy to understand. This as an opposition to the technologies that we use today, which we don't even know what is inside. Yeah? So this is also a very famous radio builder, Billy Chong. He's building radios out of credit cards. So by using the chip, this thing becomes the crystal, and this thing is the tuner. So I really recommend checking his page. It's a lot of amazing stuff if you're into crystal radio, which I am very much. So now let's see what these instruments actually do. Well, in order to receive, you would use a galena, but in order to transmit a signal, we need an oscillation. So what is an oscillation? Well, an oscillation is, a valley and a mountain, a movement back and forth, a bit like this. So in order to transmit a signal, we need this oscillation. And to produce this oscillation, basically a tuning fork in an electronic domain would look like this: a coil and a condenser, a coil or a capacitor, two components that become oscillator. So a coil generates an electromagnetic field and starts to store energy in this field. A capacitor, on the other hand, stores the energy on plates. So what happens when you connect the two? Well, feedback happens. We go back to the Ouroboros of Cleopatra. The two start to charge and discharge, and they do that repeatedly, creating a waveform, up and down. So in reality this would happen, but actually that's just a mathematical model. This oscillation starts to fade after a while, because if it was, you can think of it as a swing with a child on it. You give it a push, it goes back and forth, and then it starts to slow down unless you keep pushing. So what does a semiconductor do? What does a transistor do? Well, a transistor knows how to push and when to push an oscillation. So you have to push right at the right amount of time. So this is how oscillations collapse. And we can have a listen to that also. Is one of the devices catching radio? Yeah, I think so. I'm hearing radio. Yeah. Okay, so an oscillation collapses unless you sustain it. So in order to sustain it, you need to add additional power to it, external power. So now what we want is an oscillation that is at the same amplitude, so it's constant, right? Another way to look at it is like when you have a wheel, like this one, and you want to keep it spinning, you have to keep pushing it, right? So you can see. we needed a carrier. So in order to transmit a signal in AM radio, you would take a constant oscillation and you would start to modulate it with an amplitude. So you make it louder and quieter, let's say. You would take your voice and you would encode this carrier with your voice. So you could transmit it for far distances. So in a sense, you can say that you can make a transmitter with one stone, with a zinc side or iron pyrite, and receive the signal with another stone. Yeah. All of our hardware is mineral. Which brings me to chapter 4, computers. In the 30s, there is this one guy, Adams, that claims that he invented a transistor. He takes 3 pins this time and he attaches them to a piece of germanium, and he's able to amplify an audio signal. We do not know if this is a real claim, if the transistor was really discovered in the 30s. But he's saying so. We have some documents about it. Of course, this is 20 years before the official discovery of transistors. So before that, we had these devices. What are actually computers? This is what I was wondering back then. Like, why do we even need these devices? If you look in history, at the beginning of history, you have different civilizations that have a basic need, and that is to quantify something, to quantify time. So this is one of the earliest computers that we have. It's a clock. And the way it worked is that you would have a ball, and you had a hole inside the ball at the bottom. And you would put it in a barrel of water, and the ball would sink. The time that it would take for the ball to sink, it's a unit. So you can say that's a minute, or it's like maybe 10 minutes or an hour, so depending on the size of the ball. So you need to have somebody that was always sinking this ball, like a supervisor of the ball. Yeah. But this is an early computer. Then later on, they found this device at the bottom of the Mediterranean Sea. It's called the Antikythera, and it's a computer that this time was solving another problem, which is what is above us, so the sky. And at the same time, we have this device, which is also doing that, but in China. And we have a bit more documentation about it, because it's Susong astronomical clock. So Susong invents this device, which is a very complex mechanical computer that aims to map the workings of the sky. You would have different planets, how they align, how they move, and all would be powered by one single wheel. And this wheel would be powered by water. So he says, in this quote, he's explaining us how important it is for technology to follow the natural rhythm of fluid flow, basically. A rhythm that, of course, later on, none of our technology will follow anymore. So, of course, then there was the question of complicated operations and mathematical additions. And for this, for a very long time, we only had one computer, and that was the human computer. These are actually called the Harvard human computers, and they were the mathematicians that were calculating everything not by hand, because it's by mind, I guess. I don't know how you would say in English, by mind. And this culminated during the NASA's operation. So we have Annie Islis, who's a great mathematician, and she starts to calculate as NASA starts to launch a lot of rockets in space. She has a simple question. She's like, okay, but how would this affect our atmosphere? So she starts to calculate on paper all of these trajectories, what kind of effect they have on the ozone layer, you would say, or how it's a layer, right? On the ozone. And as time goes by, we have the first device that will replace human computers, and that is ENIAC. ENIAC is a computer produced in this country, and that this time uses a clock. So the speed of its operation is determined by a mineral. And this time the mineral is quartz. So quartz can oscillate at 100 kilohertz. We used quartz for radio telecommunications. It was used and built mostly throughout the Second World War. So here we have some of the people that were building. So as men went to war, most of the people that were left behind were women. So women started to put their hands on these pieces of technology and work in factories, making quartz crystals. So they built this massive machine. It was our first computer, not our first computer, but our first vacuum tube computer. And it's stretched up in many, many rooms. So we can imagine maybe this room 5 times, and that's the ENIAC computer. And these people that are shown there and are patching those cables, they were the first programmers of ENIAC. But for a very long time, it was said and believed and kind of communicated that these women were refrigerator women. This is the nickname that was given to them because people thought they were just models posing to make the computer more sexy. Of course, what were these women doing? Well, you see them programming the vacuum tubes. They were mostly programming the first codes that would launch the atomic bomb. And this image of the woman, refrigerator woman, presenting a sexy piece of equipment is kind of becomes prolonged until the 90s. So this is, for instance, a magazine from Bosnia about computing. I really invite you to search the other covers, they're amazing. In which in every cover we have a very, very sexualized woman that presents a piece of equipment. And if there was a computer for women, as BBC says, this is how people would believe that this computer should be in the 80s.
Now, a computer for women, how did the idea come about? I had the idea in June originally. In the next slide I don't about again. But I probably had the same dream for the next 40 or 50 nights. And I thought, yes, I'll do that. And actually, the Petticoat 5. Yes, the Petticoat 5. It's a computer made by women for women. So, let's take a look at it. Now, the first thing you notice is the shape of the keys. That's right. Their design made it easier to type with long nails. They're visible. And what is this? Well, that's a place to put your rings. And on the side here, we have a tissue dispenser. And over here, there's a piano generator which pops up when you press this button. And the space bar in the memory board. So I suppose you could fix your makeup while you work. Oh, yes, of course.
Yeah. So actually at the same time my grandmother was working with computer, not with Petticoat 5s, but with actual real punch card computers. So she was one of the first people that worked in the Timișoara's computing center, so a small city in Romania. And I dedicate these shoes to her. So in the 50s, we have the transistor being invented, or per se reinvented, by two different groups of people, one in France and one in US. The one in US is on the left. And what do they do with the first transistor? Where they hook up an electric guitar and they amplify the electric guitar. As time goes by, these transistors start to become commercially available. So we have, here we see the size of a transistor next to a cigarette. And then at some point people are like, okay, but we want more power and we want this transistor to be faster. So how about we would combine more of these transistors together to form an integrated circuit? So we take silicon, a very common mineral. It's found in quartz sand. Basically, it is the same thing as the quartz that powered or the clock of the ENIAC computer. So we take silicon, and its natural form, it doesn't look like this. We need to boil it to become this. So we would take the sand and we would put it in a very hot furnace and then melt it down, add a seed crystal inside so that this crystal starts to form, and we would get something like this. These are silicon crystals ready to be transformed into semiconductors. Why? Because silicon is a semiconductor like the iron pyrites that we are using here and the zinc plates, which means it doesn't just conduct, it doesn't resist electricity, it's kind of in a state in between, undecided, yeah, which allows all of these interesting phenomena to occur. So we would slice these crystals into wafers and then print on them different designs. This is one of the first commercially available integrated circuit, and it's made by Fairchild. Then those designs we would have to hand paint at the beginning. So here's an example of few hand painted designs for integrated circuits. Memories, different sensors that are drawn. These are all transistors that at the beginning were just made with a brush and a pen. 400 kilohertz. So we talked about ENIAC. ENIAC was 100 kilohertz. We are 4 times the speed and 4 times the capacity of ENIAC into one little device the size of our nail. This is the first microcontroller. It's called the 404 and it's put on the market by Intel. So this is a big revolution. Why? Because the whole device is a computer in itself. So this time, if the ancient computers were wondering and trying to understand the world around us by making models of it, such as the astronomical clock, or the water clocks in Persia, or later fluidic machines, different fluidic machines, this device doesn't really have a purpose. It is just there for us to imagine and to attach the purpose to it. So it's gonna build our new computers. So here we have the inside of it. We can see how it looks inside. And then, while this is being developed, there's this one guy in the lab who's hanging out. His name is Moore. And he's saying, well, you know, I think in the future, like every 2 years, these little transistors that we printed on silicon will double. The number of them will double. And because they double, they will also shrink in size. So they will become smaller and smaller and more powerful. Of course, he was saying this as a joke, but it became a reality. So today, we have nearly reached the limits of what digital machines can do. We have nearly reached the smallest transistors that we can make. And while we did that, of course, the geology of our Earth completely changed. Why? Because, well, first of all, we extracted all these materials from the Earth, and then we redeposited them on top of the Earth into a layer that kind of formed a completely new landscape.